Different Geometry by Kenji Kajiwara.
Okay, so let me thank the organizers for this opportunity. And so the title of my talk is Discrete mKdV Flow on Discrete Space Curves. And so the differential geometry is one of the source of the integral system. And I think in the first of 90s, some people developed a theory of discretizing the geometric objects such as surfaces and curves. And maybe pioneering work was done by Doriba Santini and German people such as Bobenko, Pinko, and Yuri and Wolfgang. Now the German group is now a very big group, and so doing very important works. And the topic of this talk is very elementary, one of the most elementary object in the discrete differential geometry, but I hope it's still interesting. So let me start from the, before going to the discrete space curve, let me start from the planar smooth curves. So let gamma be a arc length parameterized plane curve. So x is arc length. That means the length of tangent vector is 1. So this is a picture. And so we can introduce Fresnel frame, which is the orthonormal basis of R2 attached to the curve. So t is the tangent vector, this one. And n is a normal vector obtained simply by rotating the t by pi over 2. So this is t, and this is n. And so we have very famous Fresnel formula. Here L is this matrix and kappa is a curvature. And we can introduce mKdV flow. Something is wrong. Anyway, yeah. So we can introduce M matrix and determine the mKdV flow by this formula. Then the compatibility condition gives you the modified KdV equation here. So the kappa is governed by the modified KdV equation. This gives the isoperimetric flow of the curve. And this was done by Lam and Gondelstein-Petrich. Something wrong. Okay. Oh. So next, we go to the planar discrete curve. So what is a discrete Fresnel frame? So this is the discrete curve, and the length of the segment is arbitrary function in n. So this is length of this segment is n minus 1. This is n. Yes? So yeah. Is this what we want? Yeah. Okay. Okay, so phi n is a discrete Fresnel frame, and the discrete tangent vector is just a segment. This is a unit vector, and normal vector is just obtained by pi over 2 rotation of t tangent vector, like this. This is t, and this is n. And what is a discrete Fresnel formula? It's very simple. So here we have Tn minus 1, and we denote the angle between Tn and Tn minus 1 to be kappa n. And so this means that the flame at n plus 1 is given by the rotation of by kappa n plus 1 from the phi n. Okay, and this R is just a rotation matrix. And we can introduce discrete mKdV flow as follows. It's very simple. So we have discrete curve, and we define new point gamma and m plus 1 here, and the length of this segment is bm, and the angle between this one and this vector is w. And we can write it as follows. So this vector is obtained by rotating the Tn by this angle. This is the mKdV flow. And additionally, we require this equation. So we have all kappa n for the initial curve. Then we first give at some point we first give w0. Then we compute by this equation. We compute wn plus 1, w1, w1, w2, w3. Then we can define. We can determine all the w. And by using this w, we determine this time evolution. And this can be written as the equation of the frame in this form. M is the rotation of this angle. And the compatibility condition of these two equations gives you a modified KdV equation. Then this equation plus this condition, which gives you discrete modified KdV equation for W. Okay, so this is a discrete modified KdV flow on the planar discrete curve. Okay. Now let me go to the modified KdV flow on the smooth space curve. So gamma is a arc length parameterized space curve, similar to the R2 case, and we introduce Fresnel frame. So this is the triplet of the T tangent vector and normal vector and binormal vector given like this. And here's the definition. So this is tangent vector and this is a normal vector, and binormal vector is obtained by T cross n. Okay. Then we have famous Fresnel formula. Here kappa is a curvature and lambda is a torsion. Okay. Then we can introduce the modified mKdV flow like this. And if you put lambda equal to be 0, then we recover the planar curve. And this equation can be written down to the flame equation. So now M is given like this. And the compatibility condition of these two equations, we have modified KdV equation. So this is a famous work of Lam in 76. Okay, so we go to the space discrete curve. So first, let me introduce discrete Fresnel frame. So this is a discrete curve, okay, and the discrete Fresnel frame is tangent vector and normal vector and binormal vector. And so we consider the plane spanned by this vector, this segment, and this segment, and forget about other points. Okay. Then we define tangent vector the same, similar to the plane case. So this is a tangent t, and this is tn minus 1. Okay. Okay. So this is the length of the segment is an minus 1 an. So they are the unit vectors. So we consider this way. And this is not important, but this is an analog of the second derivative of gamma. But anyway, so we define normal vector like this. So this vector is it is important that this vector is on the plane spanned by Tn and Tn minus 1 on this plane. And this is perpendicular to T. And this is a Gram-Schmidt formula. And so this is n now. And binormal vector is defined by the T cross n. So binormal vector is here. Okay? Or you can first define Bm like this. Tn minus m, Tn minus 1 cross Tn, which gives you this one. And you can define normal vector by the Bm cross Tm, like this. They are equivalent. Okay? Then from this construction, we can write down the discrete Fresnel formula. And So this is a picture. So we have T. This is a Frene frame, and this is a Frene frame of the at the n-1. And by construction, and this B and n-1 and Bn-1 lie on the same plane because they are perpendicular to Tn-1. And we define the angles. So what does it mean? It means that this angle is kappa, is similar to the planar curve, and we define this angle to be nu, which play a role of the torsion. Anyway, and discrete Frene formula is written in this form. These are very old, and I don't know whether this is the first, but yeah, I think was the first, as far as I have investigated. This is a very old one. And the meaning of this equation can be easily seen if you write this equation in this form. Namely, so we have Frene frame at n, this is red one, and Frene frame at n-1 here. So what does it mean? It means that you first, so this angle is kappa, this angle is nu, and you first rotate like this, then you have this one. Okay, now this comes here, this comes here. And next, okay, you multiply this matrix. You rotate with respect to this axis. Then you find that now this comes here, this comes here. So we recover the Frene frame at n-1 from that one. This is the meaning. Now, so this is the discrete Frene formula. And for the Dorival and Santini introduced the semi-discrete modified KdV flow on space discrete curve. And so they have defined the M matrix like this. Then we can show that the compatibility condition gives you the semi-discrete modified KdV. Or it's rather easy to see that if you introduce the flow explicitly in this form, then this is equivalent to this one. And this gives you the isoperimetric flow of the discrete curve, and the compatibility gives you semi-discrete modified KdV equation. Okay. Now, so today I don't talk about the solution, but here's some animation. So this is a smooth curve, modified KdV flow. Two solitons interact like this, and this is semi-discrete flow. So semi-discrete flow like this. This is a two soliton like this. Okay. Now, so let me go to the discrete mKdV flow. So of course, this flow comes from the Lux pair. So let me show you the Lux pair of the discrete modified KdV. This is a 2x2 version, and L matrix is given like this, and M matrix is a little bit complicated, but given like this. Then the compatibility condition gives you these two equations, and if you eliminate kappa, then you get discrete modified KdV equation. So this is Lux pair, 2x2 version of the Lux pair for the discrete modified KdV equation. And they are in a SU2 matrix, but by the famous SU2 SO3 correspondence, we can map this matrix to the 3x3 SO3 matrix. Then this is a result. They are now very simple. L is the multiplication 2 rotation matrix. Here R is a 2x2 rotation matrix, and M is factorized into 3 rotation matrix in this form. And here mu is given by this, And if you introduce lambda, and this must be constant, and this we call discrete torsion by some reason. But anyway, so mu is given, this is related to torsion in this way. And so this gives you a discrete Frey formula, the same as the previous one, and this gives a discrete flow. And so let me, yes?
Parameter usual.
Yes. And so let me mention a little bit about the known result. And Driva-Santini considered a discrete sine-Gordon flow on discrete curves on S2. This is equivalent to the constant torsion discrete curve in R3. And they have shown on the discrete flow on the level of the flame, on the Lux pair. And yeah, actually, there are only very few works on the discrete curves. And Pinker, Springborn, and Weissman consider discrete NLS flow on discrete space curve in R3. And they characterize this time evolution by a very geometric way. And I don't fully understand, but what they say is maybe like this. So this is, here we have gamma n plus 1. This is tangent vector, and this is gamma n plus 1. So isoperimetric means that the length of the segment are the same for any m. So this and this are the same. And equidistance means that the distance between gamma and the new point gamma n plus 1 are always the same for any n. And for this deformation, so this deformation can be, so we have parallelogram. This is gamma n plus 1, this is gamma n plus 1, n plus 1. So because they are the same, so the time evolution is described like this. Okay. So this is a picture. So lengths of these are the same, lengths of these are the same. And then we can show that this always holds for this kind of deformation. This means simply that this vector is proportional to AC cross dB, and this is equivalent to EC is perpendicular to DI, and EC is also perpendicular to BI. And this is obvious because this triangle, by construction, this triangle is isosceles, so they are the same. So this is perpendicular. I is a midpoint, I'm sorry. I is a midpoint of EC. And also, this triangle is isosceles because they are the same. So this is perpendicular. So this is always the same. And they call this C as a twist parameter. And what their claim is that if Cm is a constant, then this evolution is Darboux transform, what they call Darboux transform, and is related to discrete NLS. I couldn't read further from their paper, but yeah, in our setting, as I show you later, this means that A and B must be constant. Okay, and Hochmann, he's also the Berlin group. He also considered discrete NLS flow on discrete space curves. And his construction, his claim is a little bit different. So psi to be angle between this ABD and ACD. This is written in this form. And if this is a constant, then this gamma n plus 1 is a Becklund transform, he called, and it is governed by discrete NLS. And so, in our setting, as I show you later, I will show later, but this angle is same as nu, and this can be written in terms of A and the torsion lambda in this form. And this means that his claim means that n must be constant. Okay. So anyway, these was very, for me, indirect. So I want to show the formulate discrete mKdV flow explicitly. So this is a problem. So find PQR satisfying this equation. And because this, so the length of this vector is Bm, this is unit vector. So this must be 1. So how to find this PQR? It's not trivial. And one hint is that PQR satisfy this equation. Why? So this is a picture. So by construction, you see that this vector is the sum of this vector and this vector. And at the same time, this is the sum of this vector and this vector. And from this identity, this is a consistency. So Tm plus 1, this vector, and can be written this form. And by using this definition, this can be written in this form. Then, so this is equal to this one. But this is a recursion relation, including kappa, and it's very difficult to solve unless we know some other information. But we can use it for the verification. And another hint is that PQR satisfy this a little bit complicated algebraic equation. Why? Because this is a very elementary lemma that so beta is obtained by phi rotation with this axis L. L is a unit vector. Then alpha beta can be expressed like this. This is the elementary geometry. And using this formula, because this point is obtained from this one by rotating this triangle in this like this, axis this one. So this point is obtained from this one by rotating like this. So by using this formula, we can derive this formula. And this corresponds to this one, and this term corresponds to this one, and this term corresponds to this one. And this is very complicated, and it's very difficult to solve even by using the computer algebra. But requiring some ansatz, we can solve it. And so the answer is very simple. So of course the dynamics should be deformed, but the form of this dynamic is the same as a planar curve. So this is the new point is on the plane spanned by t and n, and this is just a rotation by the angle w. This is the same as the planar curve, but the point is that lattice interval is deformed by the torsion. And if you put lambda to be 0, then this becomes B, this becomes A. This is lattice, A and B are lattice parameters of the discrete modified KdV. And so we can show that it gives the torsion preserving isoperimetric flow of a discrete curve, and this Fresnel frame satisfies this one. Okay, so the time is passing. So, and the point is that this can be checked by direct computation through the hints. Epsilon doesn't appear, but it's a lattice parameter of the it's a length of the segment of the curve. Now it's different from the lattice parameter of the modified KdV. So the point is the lattice parameters are deformed by the torsion. This is the point. And now the geometric meaning of nu and mu are very clear now. So nu appeared in the discrete Fresnel formula, and the mu appeared in the M matrix. And so this is their definition of nu and mu. Now, mu is the angle between planes A. Oh, this is very. It's not very good. Sorry. ABD and this plane. So this plane and this plane. And similarly, mu is the angle between ABD and ACD, this triangle. It's very clear. And so, how long? 4 minutes. Okay, so I will skip discrete. Yeah, we can formulate the discrete sine Gordon flow similarly, but I skip it. Sorry. Okay, here's summary. So we have the main result is as follows. So this is this dynamics gives the torsion preserving isoperimetric deformation of the space discrete curves characterized by the discrete modified KEV equation. And the point is that this equation itself has the same form as a planar curve. And this is the same as the Becquerel transformation discrete K curve. So anyway, so it should be noted that the similar formula has been obtained for the Becquerel transformation of the continuous, smooth constant torsion curve in 1996. But anyway, so this means that the Becquerel transformation is discrete time evolution, which is some kind of universal principle of the discrete integrable system, and so it coincides with this principle. And okay. And I didn't say about Schmidt formula, but the Schmidt formula holds for the discrete mKdV flow, of course. And in this case, we have to differentiate with respect to the torsion defined by the previous slide. And this gives us an explicit solution in terms of the tau functions. But I didn't have time, so next occasion I will talk about the explicit formula. And I'm sorry, I skipped discrete sine Gordon flow, but we can show a similar thing for the discrete sine Gordon flow, and it is related to discrete K surface, and also we can consider many other discrete integral systems for the curve dynamics. Okay, thank you very much.
If you introduce like new variables like tangent of the W's, probably this equation will be quite rational and recognizable.
Yes.
What it will be? H1?
I don't know the name, but it can be written in terms of rational expression. Yeah.
In the case of discrete KP, how it works?
Discrete KP, it's three-dimensional, so I don't know that. Yeah.
Two questions.
Yes.
What is the Lagrangian associated with this isoperimetric flow?
Lagrangian.
Yeah, and also the second question is, what are the surface equivalents of this? Will not go from isoperimetric, but isometric deformations of surfaces.
Yes.
So what are those equations?
Yeah. For the Lagrangian, I'm sorry that I cannot say anything about. Maybe you can ask Yuri directly. And for the second question, so how can I say? This equation itself is a very universal expression of the Becquerel transformation. You can consider the same Becquerel transformation of surfaces, and so we can do the same thing for the surfaces and motion of surfaces, deformation surfaces, and smooth deformation or discrete deformation, whatever. We can consider these kind of things.
There's some interesting link between the theory of isometric embeddings and these types of flows. So that would be interesting to explore.
Okay, thank you.
Yes. So this equation is non-orthonormal.
Yes. Yes.
Do you have any recursion operator for discrete modified KdV? Recursion operator? Because in this way, in continuous case, one can have recursion operator and
Yeah.
run the whole hierarchy.
Yeah. And actually, Tsujimoto-san has written down this kind of hierarchy, hierarchy of discrete modified KdV equation. And the recursion, maybe recursion operator can be written down explicitly, but I haven't seen it yet. But anyway.
Okay, I think it's time for lunch. So let's thank Kenji.